Hi, everyone. Thanks for coming to my talk. So the talk is about the Eureka programming model for speculative task parallelism. And this is joint work done with my advisor, Vivek Sarkar at Rice. So a general introduction. The idea here is that multi-core and many-core processors are present everywhere. They're there in server hardware as well as even in mobile devices. And what this means is that if you want future improvements in performance from your applications, you need to parallelize them. But then there's this catch situation where writing parallel programs is hard, and certainly writing performant parallel programs is even harder. So what the research community has come to do is that we can build parallel programming models that can simplify writing parallel programs and aid with productivity. And one of the most common programming models is the task parallel model. Oops. So the idea here is that you create lots of asynchronous tasks. These are lightweight, and then they run on a fixed number of worker threads, and these numbers are usually much smaller. And then the runtime is responsible for scheduling these tasks on these worker threads. And if there is any synchronization or coordination needed between these tasks, the runtime is going to handle that for you. And a common construct used in these kinds of task parallel programming models is the async and finish. It's a structured variant of fork join. So if you have an async statement, what it necessarily means is it's potentially going to run in parallel with the statements that are succeeding it. So in this case, async S1 and S2, S1 and S2 can potentially run in parallel. Right? And then you also have a join, which says that, like in this case, if there is a finish S1 and S2, S2 can only execute after all the tasks that were spawned or transitively spawned in S1 have completed. And so these kinds of constructs are commonly used in most well-known parallel programming model, task parallel models available. So IBM Extend, Chapel, Silk, OpenMP, UPC, and Habanero Java, which is the language we've developed in our group at Rice. Okay. So now coming to this construct, what are Eureka-style computations? So this Eureka programming model is meant for certain kinds of applications, and I label those as Eureka-style computations. So what are Eureka-style computations? So these are usually optimization or search problems, and the idea here is that you launch a lot of lots of tasks, and you're trying to find a result, but you don't necessarily know which task is going to give you the result, which makes them speculative. If you had known which task is going to give you the result, then you would only have worked with that task. But since you don't know, you launch quite a few, and then one of this is going to give you a result. And that point when you find this result, that's the Eureka moment. Ah, I found a result, right? And once you found a result, what this can mean is that it can cause a lot of the rest of the computation to become redundant. And so if that computation is redundant, you don't want to be doing that computation, you want to be terminating those kinds of computations, right? So this is this whole idea of Eureka-style computations, right? And so there are lots of patterns that fit this Eureka-style computation. The most common and well-known one is a parallel search. So you're trying to do a search on a data structure, and usually what you do is you partition the data structure, and you create a task to do a search on these individual partitions. And then if one of these tasks finds a result, then that's your result. You don't care about what the other tasks are going to produce. You can terminate them, right? Another example of parallel search could be like you're trying to solve a problem, and you have a bunch of algorithms to solve this problem, but you don't know which one is necessarily going to run fastest. So you launch off individual tasks to run multiple algorithms to solve the same problem. And the first one that runs the result, you're happy with that. Another example is inversion programming, right? Inversion programming, the idea is that you have this specification of a problem you want to solve, and you have a bunch of solutions, but you don't know if the solutions are buggy. So what you do is you run multiple of them, and if 2 or 3 or n of them agree on a result, you assume that, okay, then n of these couldn't have potentially repeated the same bug, so if n of these agree on the result, then that is probably my result, right? So if you had launched, like if n was 10 and you had launched 20 different solutions, if 10 of them agree, you could terminate the rest of them. Another example is branch and bound optimization. Say you're doing a search on a data structure, and you're interested in the minimal index of the occurrence of the element you're searching for. So that fits in this branch and bound pattern, where if you had launched multiple tasks, and you found a result, say, at index 100, and now you know a task that's going to compute, that's computing on indices 120 to 150. And if you're interested in the minimal result, you know that this subtask can't potentially improve the result you already know so far. So you can just kill this task off. Whereas if another task was doing a computation that might produce a result between 80 and 120, you can't kill that task because maybe it's going to produce 80, which is going to be better than the 100 you know so far. So that task needs to continue running. Right? So this is different from these other variants where you can kill all, but whereas in branch and bound, you only kill a subset of tasks. Right? And then there are multiple other examples. They're discussed in the paper. Okay, so let's start off with the simple example. It's a search on a 2D array. And I'll use this as the motivating example for the rest of the talk. Right? And I'm going to be using this finish and async construct that I presented earlier in the talk, and which are standard task parallel constructs. So in this example, what we're going to do is we have this 2D array, and what most programmers do when they're going to work with 2D arrays and they're using this task parallel model is they chunk up rows, and they launch individual tasks to work on these chunks of rows. So that's exactly what this computation is doing. In line 9, it's finding this chunk of rows, and then in line 10, it's launching a task to work on this row. And then what happens inside this task is that it iterates over all these individual rows, and then it tries to process each row, trying to find an element in the column. And so that's what process row, the method process row does in line 16. It's going to walk through the columns and try to find an element that it can match, and say if it found that match, then we're done finding the result. Right? Now, this is how most people would have written this program using async and finish constructs, but this program is actually doing lots of redundant computation. So for one, when we return from line 20, we are not signaling anywhere to the task that's running currently that you're done. So if the task was processing, say, rows 10 through 15, and it found the result in row 12, it would still go ahead and process rows 13, 14, and 15, because there is no way to return from the caller of process row. Right? So the for loop that's executing in lines 11 and 12, it would still continue running these other tasks. So the first problem is that we have redundant computation in the currently executing task, even though it knows that it found a result. The second problem is there is no way to notify other tasks that are running that somebody else has found a result. So these other tasks, they would still happily go on running and try to find the result, whether they succeed or fail. And so those are also doing redundant computations, right? Because if some task has found the result, I don't really need these other tasks to be running. Right? So there's actually two problems to solve. Right? One problem is terminating these tasks once we know that the Eureka event has occurred. Right? And the other problem is actually figuring out how to detect these Eureka events. Okay? So what most people used to do before, like until the task parallel model became popular, is use a preemptive approach to terminate these tasks. So if you know that a current task has done running and it has found a result, the way to terminate the other task is to go ahead and terminate the worker threads that are executing these tasks. Right? This pthread API has this method called cancel. You can call the cancel method, and it will go ahead and kill the thread that's running this task. The problem with this approach is, one, it's not scalable. In the task parallel model, you don't want to be killing threads and reinitializing threads, because this adds overhead to the runtime. And the second problem is, if you're going to kill a task abruptly, you don't know the point at which this code was executing. So maybe you were in a critical section and you were mutating a shared variable, right? And you kill this task abruptly. So there's no way to reason about the state of the shared variable now, because you don't know the point at which the task was terminated. Right? So this approach is called preemptive, and because of these drawbacks, preemptive approaches are usually not preferred. If there's another way out, we don't want to do a preemptive based approach. So what is the other approach? It's a cooperative approach. What happens in this approach is the task that's executing currently, it signals to the runtime that maybe you can terminate me now. Usually this is known as yield points if you're working with coroutines or handing off control to the runtime, right? Okay. So then there are a bunch of related work on how you do it in a cooperative approach. The first one is functional or lexical-based approaches. So this is used in Silk and also in the OpenMP 4.0, the latest specification of OpenMP. And the way you do it is, in this example, I've introduced a method called check. It's not necessarily called check in all these methods. They have special names, but The principle is the same. Any point you want to check for termination, you insert this call to this method check. Right? So in this case, since we are doing it a lexical-scoped, you can only insert this call inside the scope where the async was created. So in this example, you can only insert the call between lines 2 and 4. Right? If there is a method called inside this async, you cannot have this check call inside the method. So for example, in process row, we cannot have the method call check. So, and if there is a long call chain, you can't have check inside any of these points in the call chain. You need to return from all these methods in the call chain normally before you get to this lexical-scoped region, and that's the point where you can do the check. So the obvious problem with this approach is that if this call chain is going to do lots of work, then you'll have lots of redundant work in here. Right? So for example, if you were doing a search on a column and there are 1 million columns in your row, and you found the result in the first column, but you still have to wait to process all the other rest of the 1 million columns before you could return and then do the termination. Right? So it's a good approach, but lots of redundant computation still possible. A second approach is use manual termination checks. So you use if clauses all the way in your call chain. Right? If I have found the result, then return. If I found the result, then return, all the way along the call chain. Right? So problem with this approach is it's very tedious. The programmer has to go ahead and write these if blocks all the way in his code. And a drawback is if you're using library functions to which you don't have access to the source code, you can't insert these ifs there. And so then you run into the same issue that you had with the lexical-scoped approach. There are these functions from which you will not return early, and you have to wait for them to complete normally. Okay. Another approach is to use exceptions. This is used in Java threads, like this interrupted exception in the Java API, or even in the task parallel library in Microsoft's task parallel API. So the thing you do here is at the point you want to terminate, you throw an exception. And that exception is only expected to be caught by the runtime. And so if you throw an exception, the exception goes all the way up to the handler of the runtime, and then the runtime can decide what to do next. And that's how it kills the current task. The problem with this approach is you're running user code, right? So the user is free to write whatever he wants. And he can have a try-catch handler that gobbles up the exception you wanted to propagate all the way up to the runtime. Right? So in this case, the user code can interfere with the termination logic of a given task. Okay. So how do we solve this problem? Our solution is to use something called delimited continuations. It's a concept from the functional programming world. And this construct will get rid of all the drawbacks that we saw in the previous constructs, the related work that I just discussed. Okay, so what are delimited continuations, or in particular one-shot delimited continuations? It's something introduced by Matthias Felleisen at 1988. And the idea there is that you can represent a boundary for your computation that's running. And so say it's running up to some point, and you can choose to suspend the computation at a given point. What suspension means is that you're not going to execute the rest of the computation and store it away at some point in the heap or somewhere in the stack. And later at some point, you may choose to resume the computation. And when you choose to resume, what's going to happen is the runtime is going to handle putting back the computation that was there up till the point at which you suspended, and going to proceed from there on in. Right? And this notion is called one-shot because you never resume from the same point multiple times. Anytime you resume, you always make forward progress. Okay? I'll explain it with an example. So this is an example, and I'll try to explain delimited continuations here. So there is this code main, and it's going to call this execute method on an instance called delimited continuation. What happens with delimited continuations is usually have a boundary method. So in this case, the boundary method is called run. So when you call execute, execute is going to go and find the boundary method and invoke that. So execute invokes run. Then run has some code that's going to call foo and then do some printing. So it calls foo. So then foo gets added into your call stack. Then foo goes ahead and calls bar. So then bar gets added to your call stack, right? And then this call stack also has all the locals that you care about. And then in bar, we go ahead and do this call to suspend, which is going to suspend the computation. What's going to happen at this point is that the computation is going to return to the caller of the boundary method, in this case, the execute method. So as soon as you call suspend, all the state that's there in this call stack is going to get saved up somewhere in the heap, and control is going to return to the caller of the boundary method execute, which is line 4. And then it's going to go ahead and execute line 5, which is this print statement called done. So this is one way in which we avoided executing all these lines of code that were there in gray. If we so chose, we have access to this handles C, and we could choose to call c.execute again. And when that invocation would happen, what would happen is control would resume to this point at which we suspended. So control would resume to line 16, and then line 17 would eventually execute, and we would see some other prints. And then normal returns would happen in the call stack. Right? But in our case, we don't care about resuming a delimited condition all over again, because we want to terminate a task. Right? So at the point we suspend, we're done. We don't need to worry about storing all the locals and having to resume the computation. And so the idea with the task termination is that we're going to have a runtime that's going to hide the use of delimited continuations. We're going to hide the use of these boundary methods inside the runtime, and also the use of the suspend methods inside the runtime. So the end user or programmer never actually sees these delimited continuations, or is not necessarily aware that they're being used. And there's good reason for that, because delimited continuations are pretty complex, and that's the reason they're not very commonly used in the regular programming world, right? So we are hiding away the use of delimited conditions from the user just to simplify their job or task. And so how do we terminate a task? Anytime we want to terminate a task, we have this method called check, and then check goes ahead and does the necessary logic, checking if this task needs to be terminated. If it has to be terminated, then suspend the computation. So if you call suspend, then control returns to the runtime, and then the runtime can choose what to do next. Okay. So the next issue is how do you detect these Eureka events? So all the previous work that I mentioned, this lexically scoped exceptions or manual returns, they only handle one kind of pattern. That's the parallel search Eureka. They don't handle all the other variants that I mentioned to you. So we want a construct that's abstract enough to handle all these different patterns. And what we've come up with is a Eureka construct that has a simple life cycle. It starts in a new state, which means it's uninitialized. And then it can transition to an updating state, where it has a temporary value. And finally, it can transition to a resolved state. When it's resolved, it's done. So you're never going to update the value of the Eureka further after the resolved state. And so notice that there is this monotonicity in the state transitions, right? So if you're doing a search, for example, you start off with an uninitialized state, and once you found the index of the element in the array, you jump to the resolved state. If you were doing this branch and bound, where you're, say, interested in the minimal value, then you're always in a temporary updating state. And eventually, when you know you found the result, you jump to the resolved state. Okay. So then, now that we have this Eureka construct and then our approach of terminating tasks using delimited continuations, we can propose the Eureka programming model. So the Eureka programming model will be an explicitly parallel programming model, just like async finish. It's going to be an extension on async finish, so we will have some added constructs. We will allow tasks to register on these Eureka instances that we spoke about, and we will also allow programmers to define their own Eureka constructs. So I mentioned to you 8 or 9 different patterns of Eureka style computations, but maybe a user identifies another pattern. So our programming model allows him to define his own Eureka style of computation. And then we want this programming model to simplify the task of writing Eureka style computations. Right? That's the whole idea of parallel programming models. We want the user to have reduced complexity to worry about and simplify the task of writing programs or parallel programs. Okay. So what are the extensions that we have? So this finish that I showed earlier, the only extension to the finish construct will be that we have a new Eureka construct that we can register on a finish. So in this case, we have this finish, and then you registered the Eureka, and then you have the body that you want to execute. And so all the statement that's going to execute inside this finish scope are going to be automatically registered on the Eureka instance that we pass to the finish. There is no change to the async statement. That's because every async runs inside some finish. So if a Eureka is registered on a finish, the async can inherit that registration of the Eureka. And then we have two new method calls. One is offer. Offer is the means of identifying a Eureka event. So anytime we find a result, the offer method is the method that we're going to call to notify that we found a result. And then we have this check method that allows you to check for termination in your task. So anywhere you have a check call, the runtime is going to make sure that it finds the Eureka that you're registered on, and it's going to check if the Eureka is resolved, or should this task continue executing, if not, terminate the task. Okay. And then all the runtime now needs to worry about is mapping these Eureka instances to finished scopes. And what you have on the left, the finished scopes and then tasks, these are normal constants that you have in an async finish programming model anyways. The program needs to keep track of which finish a task is registered on. The only added overhead here is now you have to also keep track of which Eureka instances a finish is registered on. Okay. So given this programming model, how can we write the same example that I spoke about earlier? Right? I want to do a parallel search on a 2D array, and I want to be able to terminate tasks early when I found the result. So if you remember from the previous slide, the only changes that happened here is that now we have this Eureka factory. Previously, we had an atomic ref factory to store the result. Now we have a Eureka factory, which is going to create the Eureka that's going to store the result. In line 7, the change is that the finish now registers on a Eureka. There is no change to lines 8 through 11. It's the same code that we had. We have these chunks of rows, and we are spawning asyncs to do a search. In the method process row, the place where we were updating the result, now we have that replaced by an offer call. That's how you notify that you found a result. And we have this added method called check for this cooperative termination. Any place we want to check for termination, we have this call to check. Right? So that's the only difference from the async finish program. So effectively just 3 or 4 lines. Yes?
Why do you pass the error and C to check?
Sorry, come again?
Why do you pass an argument to check?
Okay. So let me answer that in a couple of slides. Okay. So the question was, why does check need an argument? Okay. So the reason check needs an argument is that if you're doing a search, you don't care about the argument. But if we're trying to find the minimal index, then you need to know what is the bounds that you're searching for currently. Right? And if that bound is greater than the minimal value you already know, then you can just effectively terminate the computation. Or if you were doing some search like an engine, you want to run the computation for 10 seconds, and if already overshot the boundary, then check can be used to trigger that. Okay, so this slide is basically saying that the same code snippet that I showed you earlier, you can just change the Eureka factory, and you can get different behavior from the code just by changing the Eureka that you're registered on. Right? So you can have this parallel search, you can have any of the k-count search, branch and bound, engines, and so on. Okay, so jumping on to experimental results. So we ran our benchmark programs on 32 cores, so 32 worker threads eventually. We implemented all the variants of related work that I mentioned to you earlier, as well as our Eureka programming model. And we then compared the performance and some productivity metrics. Right? Okay, so in terms of performance, in this case, the red bar is just a pure async finish program with no early termination of tasks. So as expected, this is going to do lots of redundant work, so this will be the highest bar in this chart. So effectively, all the benchmarks, this is the highest bar because it's doing lots of redundant computation, which we could have saved, right? The blue bar is the lexical-scoped or function-scoped. As I mentioned earlier, you can't return early from this call stack if you have one in this lexically-scoped. So in this variant, you can do better than async finish, but that's not necessarily the best you can do. And that's exactly what the graph shows. The blue bar is usually between the red bar and the other variants. The other variants, exception-based, cancellation token, and our model, Eureka, they effectively do all the same thing. None of these benchmarks exhibit any of the problems that I mentioned to you about exceptions and cancellation tokens. So we didn't have library functions and so on. We did that just to ensure that the comparison was fair for all the benchmarks on all the different variants, right? And the takeaway from this slide is that our model performs at par, if not better, than the other approaches, exception-based and cancellation token, right? So first thing is we are not sacrificing performance using our model, right? any of the other models that you had, including manually written code, we can achieve the same performance. So then the next goal is, can we be more productive? Because we're doing a programming model, we're not sacrificing performance, we want to be more productive, otherwise why will users want to use our model, right? So we use 3 metrics. One is lines of code, I'm not covering that in this slide. The other 2 metrics were cyclomatic complexity and Halstead's development effort. So cyclomatic complexity basically measures the different amount of paths in your program. So effectively, what are the paths that the programmer has to worry about, and that can make the code more complicated to reason about. So on average, our complexity was 10% better than the other 3 approaches that performed better or close to us. So cancellation token, exceptions, and function scoped, we were on average 10% better in terms of cyclomatic complexity in the code. And we were worse than async finish, but async finish doesn't have any of this early termination check, so that's expected. But it performs really poorly, as shown in the previous slide. So we will not be using async finish anyways to write Eureka-style computations. And then the other metric is Halstead's development effort. This basically counts the number of tokens in your programs and frequencies of these tokens, and that does some arithmetic to figure out how hard or easy it was to write a program. And this is a useful tool to compare implementations of the same algorithm in the same language, right? So, and since we were writing in Java, all these variants were written in the same language, so it's a fair comparison to use this metric. And again, we were around 15% better than exceptions, cancellation token, and function scoped approaches. So nearing towards the end of my talk, what's there more in the paper that I have not covered in this talk is that there's description of the different Eureka patterns, implementation details. We also have an artifact that has been accepted, and the source code for the benchmarks and our implementation is there on GitHub. I did not cover 2 important parts. One is using component composition. So say I have 2 Eureka constructs, can I create a new Eureka construct based on these 2 Eureka constructs? So that's discussed in the paper. And then using functional decomposition for reusability. So say I have the code to do a search on a 2D array. Can I use this code to do a search on an n-dimensional array, for example? And then other performance and productivity results are also there in the paper. So to summarize my talk, I presented what Eureka-style computations are and different patterns of them. I proposed the Eureka programming model, which is a simple extension of the async finish model, and how we do task termination. Evaluated our approach, and one thing I didn't mention is our implementation runs on an unmodified JVM. So we have to, and the JVM doesn't support delimited continuations, so we have to mimic support for delimited continuations and do all the compiler magic needed while compiling your code to support continuations. And we can get good performance even on unmodified JVM. So if the JVM actually supported delimited continuations natively, we would get even better performance. Right? And then we displayed productivity benefits using this cyclomatic complexity and development effort metrics. So that's the end of my talk. I'm happy to take more questions.
Hi, 2 questions. One is, so you use what you call one-shot delimited continuations, although they're not really because you never continue from it.
Yes.
It seems like what you really want is just exceptions that aren't caught by the user code. That's really all you're going for.
Right, but I don't want to pay the performance penalty of using exceptions either.
Well, that's an interesting question of what the performance penalty is in the case that you're aborting, because you're only, exceptions are fairly low overhead except when you trigger them, which is going to be once for cancellation. But
you can I answer this before you go to the second? So you can imagine a scenario where you create millions of tasks, right? And then you have to abort, say the first task produces the result. So you have to effectively abort 1 million tasks and create 1 million exceptions.
So related to that, though, what happens, for example, to resource cleanup? So if you used exceptions, then finally blocks would be triggered to clean up resources. What happens here?
So since this is a cooperative check, you only insert these calls when you know that you can do the cleanup. So for example, if you're running inside a critical section, you can't invoke these methods inside.
But then in practice, before you invoke the method, you first have to check if you're going to be using the method, clean up, and then invoke it.
Yes, something like that. So that's a limitation of this approach.
Right. So the other question was, I'm just surprised that you said the exception version has a much higher, I guess, developer overhead, because in some X10 code, I've actually implemented exactly this technique at the user level for code that needed early termination. It pretty much looked exactly like the code you have there, except that I didn't magically get an object register with a finish, so I had to pass an object through methods. Other than that, it's just you pass an object that you call check and throw cancellation exception if it's supposed to be canceled, and you have code that propagates that and cleans it up. It looks very similar.
Yep.
So I guess where does the additional complexity
But if the
come?
user had try-catch blocks, which you can't control, then your exception logic is messed up, right?
True, although they may actually want to abort the failure temporarily to clean things up and then continue it, but yes.
So that's the whole point.
Okay. So you talked about, you gave this new name, Eureka and all that. To me, it sounded like phasers with a check. So it has, so your verify is like your signal, and then you have a check. So you have reached a state that you signal, and the check is just one more. So it's like phasers. So what's the difference?
The difference is that you want to be able to terminate early. Right? With phasor-based computations, you would run the computation to the completion.
No, you don't. So the check does it. So the check is kind of, now the check will throw an exception. So instead of, so now I have a phaser where the check will throw an exception, which is caught, I mean, it's kind of extending on his question that internally, it's a phaser with an exception. Isn't it? Or I mean, you could probably implement it some other way too.
So that's twisting the meaning of what phasers are meant to be. Phasers are meant to represent phased computations. These are not necessarily all phased computations.
This phased computation with termination. That's what exceptions are giving you.
So,
I'm trying to understand if there is something more that's not.
no, it's basically doing the same thing that exceptions are, but just simplifying writing programs in that manner, right? And also supporting these various patterns.
It seems that you have a data race.
Sorry, come again?
It seems that you can have races. So you finish, the finish construct returns when an offer has been done, right?
No, the finish construct returns once it knows all the asyncs that have been spawned inside have been terminated.
So even if you register a Eureka with it?
Okay. If you register a Eureka and say the Eureka has been resolved, so if the Eureka has already been resolved, then that finish is a no-op because the Eureka is already resolved. If the Eureka was not resolved and you spawned asyncs inside the finish, then you wait until all these tasks have been terminated, either without executing them ahead of time or while they were executing.
Okay.
Thanks for the talk. It just occurred to me that I think there is a fundamental difference between exceptions and Eureka, because when you throw an exception, you only that affects only the call stack of the current thread. Whereas in this case, if you say Eureka, you will actually
also terminate
that has an effect on all the other tasks, right?
Yes.
Because you want to also avoid the redundant computations of other tasks.
Not if it goes with the phasers. Because the phasers, if someone signals with a phaser and the other threads kind of get the signal and then it's a cooperative
Yes.
exception.
So
Okay, so I was not talking about phasers. I was talking about if you don't have phasers and you only have async finish and exceptions, then just as a
But even then, your top level, where you were registering the continuation now, that same place, use a library, it takes about 10 lines to write, which does the propagation for you. You write it once, it's not hard code in any of these languages.
that's easier said than done. So I'm not convinced, but maybe you have more experience. I was just making a comment. I'm not trying to solve the whole discussion here, right?
and there are restrictions with use of phasers, right? There is this finish async restriction. You can only pass the phaser down the finish scope. You cannot pass it to another independent finish scope. Say you created a Eureka in one finish scope and you passed it as an argument to another finish scope. That's not nested in the same hierarchy. There's a restriction with that, with phasers. No, that's not an RD. That's required for deadlock freedom for phasers.
So just to continue the discussion after this session,